Hello and welcome. Today we're going to be looking at what exactly happens when you do an operation such as addition on two Numpy arrays of different shapes. By the end of this video, you're going to understand why in this case you should expect a 3x3 array, and you're going to understand where those numbers come from, and you're going to understand what you would need to do differently if you actually wanted to just add number by number 0 plus 3, 1 plus 4, 2 plus 5. So what is array broadcasting? Array broadcasting is a way to do element-wise operations on arrays of possibly different but compatible shapes. For example, in this case, I have a matrix with 2 rows and 3 columns, and I have a single row of 3 numbers. In this case, it's pretty clear that I can simply add this row, 1, 2, 3, to the top row and the bottom row. When I add it to the top row, I get 1, 3, 5, and when I add it to the bottom row, I get 4, 6, 8. Similarly, if I added a column 1, 2 instead of a row, then I would just add that column to each column. This idea works with any kind of element-wise operation that you would want to do on arrays. So you can think plus, minus, times, exponentiation, taking the minimum or maximum element-wise, or lots of other different functions. If you're not sure whether a certain function uses this kind of array broadcasting, just search for the word broadcast in its Numpy documentation. Before we can go on to decide what it would actually mean to add these two different arrays in a more general context, first we have to understand what it means for the shapes of these two things to be compatible. Obviously, I can add 1, 2, 3 as a row, but would I be able to add 1, 2, 3, 4 as a row? Well, no, that doesn't really make sense. And it's kind of obvious why, but it's still hard to explain. So here are the rules for determining if the shapes of two arrays are compatible. It might look like a lot at first, but stick with me. I promise we're going to do a lot of examples, and once you see a few examples, the rules are going to be crystal clear. First off, if one of the arrays has more dimensions than the other, then when you look at their shapes, you should right align them and imagine prepending ones to the shorter one. So if you had an array which is just 3 numbers, then you could just as well think about it as a 1 by 3 array, or a 1 by 1 by 3 array, or a 1 by 1 by 1 by 3 array. It doesn't matter how many ones you prepend to the front of the shape. That doesn't change that there's just 3 numbers in there. The next rule is that if an axis has just a single element in it, then you can repeat or broadcast that axis to the length of the other vector's axis. All remaining axes must have the same lengths. So using these rules, we'll be able to compute whether arrays are compatible, and if so, what the broadcasted shape, the results of the broadcasted operation, will be. Again, these look a little complex, but once you see the examples, it'll clear right up. So here's the first example. We start with an x that we assume has shape 2 by 3. Of course, something with the exact same shape must be compatible. So in this case, another 2 by 3 array would be compatible. But there are definitely other things that are compatible. So we could have a 2 by 1 array, and we see that that's compatible because the 2's match, and then 1 can match with anything, so the 1 matches with the 3. That's okay. Similarly, a 1 can match with a 2, and a 3 can match with a 3. Those are compatible. And whenever you see something that's shorter than the other one, you prepend ones until they're the same length. So you should imagine that it looks like this, in which case it's the same as the previous thing. The 1 matches with the 2, and the 3 with the 3. So in that way, if I have an array of just 3 elements, that still matches with a 2 by 3 array. In this case, the broadcasted shape is going to be 2 by 3. Now, what are some examples of things that are not compatible? Well, a 3 by 2 is not compatible because a 3 doesn't match a 2, and also a 2 doesn't match a 3. We are not allowed to reorder the axes when checking for compatibility. In this last example, you might think that it would be compatible because it's like a 2 by 1, but not so. The rule is always to prepend ones. So if I do that, I add a 1 at the beginning, not the end. In that case, I would have something that looks like 1 by 2. The 1 matches with the 2, but the 2 does not match with the 3, so they're not compatible. If you wanted to do 2, 1 instead, you would just have to reshape y using the dot reshape method. Let's look at another set of examples. In this case, we have 4 dimensions, and we see that all of the following things are compatible. In every case, we follow the same rules. Again, though, in this case, we cannot append a 1 to make it compatible. We always prepend ones. So far, we've only seen examples where the resulting shape is the same as one of the original shapes. Let's look at an example where that is not the case. In this example, we have quite different looking shapes, but they are in fact compatible. You can see in this case that I've already right aligned them and that they match up. Every entry either is the same number or has a 1 in the column. And then, of course, I would just prepend 1s in this space, but I'll leave that out. So the way that we're getting the common shape is to take either the common number, in this case 17, or 1, or if only one of the numbers is 1, then take the number that's not that. So we would take 17 here, 1 here, 11 here, 7 here, 5 here, and then 3, 2, and 1. So now you should be able to tell, just by looking at the shapes of the two arrays, whether they're compatible, and if so, what the resulting shape should be. But I still haven't told you how to actually add two things of different shapes. To do that, all we have to do is imagine a for loop. The idea is that for any dimension where you used a 1 to match a different dimension, then instead of looping over that variable, just use index 0 because that's the only valid index. In this case, I have a 3 by 3 and a 3 by 1. So we check that the shapes are compatible. 3 matches with 1 and 3 matches with 3. The resultant shape should be 3 by 3. I then create an empty array of that shape, and I'm going to use nested for loops to fill in the values. Of course, actually using these for loops would be a bad idea because for loops in Python are extremely slow. But to understand what value Numpy is actually computing when you do this, this is what you should be thinking of. Okay, so in order to fill out the ijth entry of our output array, just think that you want to do element-wise addition, but when it's not possible, fill things in the best possible way. X has shape 3, 3, so it makes sense to give I and j as indices to the X array. Y, on the other hand, was 3 by 1, so it makes sense to pass in the I index, which goes from 0 to 2, but I can't pass in the j index here because that axis only has one element. It only has one valid index, so just use it. If I go ahead and run the code, we see that the output is the same as what Numpy gave. Let's take a look at another example. This example shows how to think about it when you had one array that didn't have as many dimensions as the other. And the rule here is just omit the variables whenever you prepended 1s to the dimension. In this case, I have X, which is a 2 by 3 by 3, which is essentially it's two 3 by 3 matrices. There's one, and there's the other. And I have a single 3-element array. We right align the dimensions, and we can tell that they're compatible. 3, 3, 3 matches 1, and 2 matches 1. And the resultant shape is 2 by 3 by 3. This time I have 3 nested loops because the shape is 3-dimensional. To figure out what goes in the ijk spot of the output array, we just look at what to do for each element. X has no problem because it has shape 2 by 3 by 3. But with Y, there's only one dimension. So what to do with the first 2 dimensions? Well, since they were pretended to be length 1 anyway, all we were going to do is plug in zeros there. So let's just omit them. The way that I know to plug in k here instead of I or j is that I'm thinking of this column as corresponding to I, this column as corresponding to j, and this column as corresponding to k. So you can see that for y, I have enough dimensions to plug in the index. Again, when I run the code, you can see that the output of the Numpy calculation is identical to the output created using the for loops. In this final example, let's look back at the one that we started with. On the title slide, we had a 3x1 array and a 1x3 array. This highlights the fact that you can have ones in either of the arrays, not just one of them. By now, we can calculate the compatible shape. 3 matches with 1 and 3 matches with 1. So the resultant shape will be 3x3. So we create an empty array of that shape and loop over the 2 dimensions. The output at ij is computed as follows. The first dimension corresponds to I, and we know that in that dimension, x has the same shape as the output, so it makes sense to plug in the index I there. But for j, x only has one thing in it, so let's just use the only valid index, 0. On the other hand, for y, it is the I dimension that only has one valid index, so we plug in 0, but for the j dimension, we can plug in the index j. So now we see where this 3x3 answer comes from, and you can check that our answer is the same as the NumPy one. So now can you tell what would you do if you wanted to just add 0 and 3, 1 and 4, and 2 and 5? Well, the answer is you would just reshape one of them. You could either reshape this one to 1x3 or this one to 3x1, or both of them just to a 3-element array. Well, I hope this video helped you understand a little bit better about what NumPy array broadcasting is and why it gives you the answers that it does. If you're looking to test your skills a little bit, here's an exercise for you. Suppose you have 1,000 images that are 32 by 32 pixels, and each image has 3 color channels. So it's your standard red, green, and blue pixel values from 0 to 255. So every pixel has a red value, a green value, and a blue value. Now suppose you have all this image data stored in a single array of size NCWH. Here N is your 1,000 images, C is the 3 channels, W is the width, and H is the height. So my question for you is, what array Y would you multiply by to scale every red pixel by 2, every green pixel by 3, and every blue pixel by 4? If you want to check your answer, check out the GitHub link in the description, which has the source code for this notebook. Thanks for watching. Don't forget to like, comment, and subscribe.